Welcome to Science to Sleep By. Wherever you are, maybe lying in bed, the lights dimmed, your room quiet, I invite you to take a slow, deep breath and let it out gently. Tonight, we're going to drift beyond the stars, past the glowing trails of the Milky Way, beyond the galaxies spinning softly in the dark. We're going to explore something you can't see, something you can't touch, and yet, it holds the universe together. It's called dark matter. For decades, scientists have searched for it not with their eyes, but with their equations, with telescopes that can see the invisible, and with instruments that listen for whispers from the cosmos. Dark matter doesn't shine, it doesn't glow, but its gravity bends light, moves galaxies, and shapes the universe in ways we're only beginning to understand. So tonight, as you settle into the quiet rhythm of your breathing, let your thoughts wander gently across the stars. Let's uncover the story of the universe's hidden mass, the dark matter of space. Keynote 1. The hidden weight of the cosmos. When you look up at the night sky, what you see feels infinite, a black canvas sprinkled with stars that shimmer faintly from impossible distances. There's a calmness in that sight, the quiet reminder that the universe stretches far beyond what we can reach. For thousands of years, humanity has gazed at those same stars, believing that what we see is all that exists. But the truth, discovered only in the past century, is that the visible universe, every star, every planet, every glowing galaxy, is just a tiny fraction of what's really out there. The rest is hidden, not in plain sight, but in the vast, invisible framework that binds the cosmos together. Scientists call it dark matter, and it makes up most of the matter in the universe. The name sounds mysterious, almost poetic, but it's not meant to describe something sinister. It simply means we cannot see it. Dark matter doesn't emit or reflect light. It doesn't absorb it either. To our eyes and even to our most powerful telescopes, it's invisible, yet its influence is everywhere. It exerts gravity. It shapes the motion of galaxies. It decides how stars cluster, how galaxies collide, and how the universe holds itself in balance. It is the unseen architecture beneath the glittering structure of the cosmos, the hidden weight of everything. Imagine the Milky Way, our home galaxy, a vast spiral disk made of hundreds of billions of stars. When astronomers first began measuring how fast these stars orbited around the center, they expected the outer stars to move more slowly than those near the middle. After all, the visible mass, the glowing core, the bright stars, the gas cloud should determine the speed of those orbits. Just as planets closer to the sun move faster because they feel more of its gravitational pull. But the numbers didn't fit. The stars far from the galactic center were moving much too fast, so fast that by the laws of physics, they should have been flung out into space. And yet, they stayed. Something unseen was holding them in. This was the first whisper of dark matter, a presence that couldn't be seen, but could be felt. It was as though an invisible hand was wrapping itself around the galaxy, keeping everything bound. The visible stars and nebulae were just the faint decorations floating in a much larger, heavier halo of invisible material. This halo, scientists realized, must make up the majority of the galaxy's mass. Without it, galaxies like ours wouldn't even exist. They would simply tear themselves apart under their own motion. To understand just how dominant dark matter is, consider this. If you gathered all the light from every star, every glowing nebula, and every planet in the cosmos, it would add up to less than 5% of the total universe. That means more than 95% of what's out there is invisible, composed of dark matter, and something even more mysterious called dark energy. Everything we've ever seen, from the sun to the most distant galaxy captured by the Hubble Space Telescope, is just a small trace of cosmic reality. The rest hums quietly in the background, unseen but essential. There's something humbling about that realization. As you lie there, breathing softly, maybe picturing the night sky stretched above you, imagine that the universe you see, all that beauty, is only the surface. The stars that twinkle are like islands rising from an ocean of darkness. Beneath them lies a vast sea of invisible mass, a silent field of particles we cannot touch, but whose gravity sculpts the heavens. Every galaxy floats within this invisible sea. tracing its shape like leaves drifting on a hidden current. Our knowledge of this hidden universe came not from direct sight, but from the delicate fingerprints it leaves on the motions of cosmic objects. Astronomers have spent decades studying how galaxies rotate, how clusters of galaxies move, and how light bends as it passes through space. These clues, subtle but consistent, all point to the same truth: something unseen holds more weight than everything we can see. The universe is, in its truest sense, an iceberg, and we live only among its visible peaks, while the vast majority lies beneath the surface, forever hidden in shadow. The idea of dark matter also challenges our understanding of what matter even is. Everything you can touch, the air you breathe, the chair beneath you, the atoms in your body, is made from ordinary matter: protons, neutrons, and electrons. But dark matter, whatever it may be, doesn't seem to interact with light or normal atoms in any known way. It doesn't glow or burn. It doesn't collide or scatter like the matter we're familiar with. It simply passes through, silent and unseen. If you could somehow hold a piece of it in your hand, you wouldn't even know it was there. It would drift through your skin, through your bones, through the entire Earth itself, leaving almost no trace. And yet, without it, galaxies would unravel, stars would scatter, and the cosmic tapestry would lose its form. The balance between what is visible and invisible is what keeps the universe together. The delicate glow of stars depends on the heavy hand of darkness. It's remarkable to think that the discovery of dark matter didn't begin with new technology, but with curiosity. Astronomers like Fritz Zwicky in the 1930s noticed galaxies in clusters moving too fast to be bound by their visible mass. Later, in the 1970s, Vera Rubin's careful measurements of galaxy rotations revealed the same mystery: an invisible halo surrounding every galaxy. These scientists weren't chasing fantasy. They were simply following the numbers. And the numbers whispered that something more existed, something vast, unseen, and patient in the stillness of night. When the mind quiets and the imagination drifts, it's almost comforting to know that the universe hides more than it reveals. The darkness isn't empty. It's full. Every patch of night sky, no matter how deep or black it looks, is woven with threads of invisible matter, gently tugging at the stars. The Milky Way, Andromeda, the faraway galaxies shining like distant lanterns, all of them are tied together by this unseen cosmic web. If you could see dark matter, the universe would appear not as a dark void dotted with light, but as a glowing network of filaments stretching endlessly across space, with galaxies hanging like dewdrops along its threads. This hidden weight of the cosmos is what gives structure to everything. It is the foundation upon which galaxies are built. It shapes the very map of the universe, guiding light and gravity through invisible hands. It's the secret scaffolding that holds the stars in place, the unseen balance that lets beauty exist in form and motion. When you close your eyes and imagine the stars, imagine too what lies between them. The silence that isn't empty, the darkness that isn't nothing. Somewhere out there, beyond the reach of light, lies the true mass of the universe, waiting quietly to be understood. If you could peel back the glowing surface of the universe, if you could strip away the stars, the nebulae, and the radiant clouds of gas that fill the galaxies, what would remain would not be emptiness. Beneath the light lies a vast, silent structure that cannot be seen, cannot be touched, and yet shapes everything that exists. This is dark matter, the invisible glue of the cosmos. It is a presence that defies our senses, and yet defines the universe we live in. To understand dark matter is to accept that most of reality hides in plain sight, beyond the reach of light. The name itself, dark matter, is both simple and profound. Dark, because it does not emit, reflect, or absorb light. It is invisible to every telescope, no matter how powerful, whether it observes invisible light, X-rays, radio waves, or infrared. Matter, because, despite its invisibility, exerts a pull. It has gravity. It bends the fabric of space, tugs on stars, and influences galaxies as if it were made of something real, something with mass. In the simplest sense, Dark matter behaves like ordinary matter that has been stripped of all its light, but the truth is, dark matter is not ordinary in any way we know. Every particle of normal matter, the atoms that make up your body, the air around you, the oceans, and the sun interacts with light. That interaction is what allows us to see the world, to sense heat, to detect color and texture. Dark matter does none of this. It passes through light as if light were not even there. It passes through you, through the earth, through the planets and the sun, almost as if the universe were transparent to it. If trillions of dark matter particles were streaming through you right now, you would never know. You would not feel a thing. This raises a haunting question. If dark matter cannot be seen or felt, how do we know it's there? The answer lies in the one force that still connects it to everything else: gravity. Dark matter reveals its presence by the way it bends and pulls on the things we can see. Just as you can feel the wind by watching leaves move, even if the wind itself is invisible, astronomers can feel the pull of dark matter by observing how stars and galaxies move under its influence. Gravity is the only messenger that dark matter sends, the only clue it leaves behind. One of the most compelling pieces of evidence for dark matter comes from how galaxies rotate. When scientists measure how fast stars at different distances from the galactic center move, they find something surprising. Instead of slowing down with distance, as Newtonian physics predicts, the stars continue to move at roughly the same speed, even far from the bright core where most of the visible mass resides. This suggests that the galaxy is surrounded by an enormous halo of unseen material, something massive enough to keep those distant stars in orbit. Without this invisible mass, galaxies would spin themselves apart, scattering their stars like sparks into the night. Another powerful clue comes from gravitational lensing, the way light bends when it passes near a massive object. According to Einstein's theory of general relativity, gravity warps space itself, and light follows that curvature. When astronomers observe clusters of galaxies, they notice that the light from more distant galaxies behind them bends and distorts in strange, graceful arcs. The amount of bending, however, is far greater than what the visible mass of the clusters can explain. The only way to account for it is to assume that most of the mass is invisible dark matter, once again revealing itself, not through light, but through gravity's quiet curve. Scientists have even simulated how the universe formed under the influence of dark matter. When they model the early universe shortly after the Big Bang, adding only the known forms of matter, the resulting cosmos looks nothing like what we see today. But when they include dark matter, everything suddenly fits. The galaxies form in the right shapes, the clusters arrange themselves correctly, and the large-scale structure of the universe, that vast cosmic web of filaments and voids, appears just as we observe it. Without dark matter, the universe would look entirely different, more chaotic, less structured, almost empty. So what, then, could dark matter be? The honest answer is that we don't yet know. It could be made of undiscovered particles, tiny, stable entities that rarely interact with ordinary atoms. The leading candidates are known as WIMPs, short for weakly interacting massive particles. These hypothetical particles would have mass, giving them gravity, but would interact so weakly with other matter that they'd pass right through almost everything. For decades, physicists have searched for WIMPs using sensitive detectors buried deep underground, shielded from cosmic rays and background radiation, hoping to catch just one faint interaction. So far, none have been found, but the search continues. Another possibility is that dark matter might be composed of something even more exotic: particles called axions, predicted by certain extensions of quantum physics. Axions, if they exist, would be incredibly light and abundant, moving through the universe like a vast sea of invisible waves. Some scientists even speculate that dark matter might not be made of particles at all, but could arise from an entirely new kind of physics, perhaps from hidden dimensions, primordial black holes, or fields that ripple through the fabric of space itself. Whatever its nature, it lies beyond the current boundaries of our knowledge. The fascinating part is that dark matter doesn't clump together the way normal matter does. Ordinary matter can cool, collide, and condense to form stars and planets. Dark matter doesn't. It remains diffuse, spreading out to form halos that extend far beyond the edges of galaxies. It's like a silent scaffold that gives structure but never shines. The galaxies we see, glowing with starlight, are only the brightest nodes in a vast dark network. They form where dark matter's gravity pulls ordinary matter into dense regions, where gas collapses, ignites, and begins to burn as stars. In this way, dark matter is not only the framework of the cosmos, but also the midwife of light itself. It creates the stage upon which the visible universe performs. Think for a moment about how astonishing that is. Everything visible, the galaxies, the stars, the planets all exist because of something invisible. The universe we see is not self-contained. It is shaped, guided, and sustained by what we cannot see. The darkness between the stars is not nothing. It is the foundation of everything. In the grand balance of the cosmos, light depends on shadow. If you could somehow tune your senses beyond light, beyond radiation, and see the gravitational contours of the universe, you would witness a structure far more complex and magnificent than any star map. You would see filaments stretching like rivers across space, connecting galaxies in clusters that shimmer faintly along invisible threads. Between these filaments lie immense voids, regions almost entirely empty, where dark matter's pull is weaker. This cosmic web, woven from dark matter, is the true shape of the universe. It is the hidden skeleton that holds the galaxies in place. The quiet architect of creation. As you lie still, imagining the stars hanging in their invisible lattice, you can almost sense the serenity of it all. The universe is not chaos, but a vast harmony of forces, some bright, some unseen. Dark matter is one of those unseen symphonies, playing a melody we cannot hear, but can feel in every motion of the cosmos. It reminds us that visibility is not the same as presence, that the most powerful things are often the ones we can't see. It humbles our certainty, softens our perception, and expands our imagination beyond light itself. The story of dark matter's discovery begins not with a blinding flash of revelation, but with small, patient questions asked by astronomers staring at the night sky. It was never discovered in a single moment, never caught in a telescope's lens or captured in a detector. Instead, it was revealed through whispers, tiny inconsistencies, curious patterns, and quiet defiance against the laws of visible matter. It was found, not by sight, but by inference, in the subtle tug of gravity and the strange motions of galaxies that refuse to behave as expected. The discovery of dark matter is one of science's most beautiful paradoxes. We found something invisible by watching how it shaped everything we can see. The first hint appeared in the 1930s, when a Swiss astronomer named Fritz Zwicky began studying the Coma cluster, a vast collection of more than 1,000 galaxies located over 300 million light-years away. Zwicky was fascinated by the way galaxies moved within this cluster. He measured their velocities using the redshifts in their light, expecting that the cluster's total visible mass, the combined gravity of all the galaxies, would be enough to hold them together. But the numbers refused to fit. The galaxies were moving far too fast. According to Newtonian physics, if their visible mass was all there was, those galaxies should have flown apart long ago, scattering into intergalactic space. Yet the cluster remained intact, bound together by something unseen. Zwicky called this missing substance Dunkelmaterie, German for dark matter. It was a radical proposal for his time. Most of his peers dismissed the idea, thinking perhaps his measurements were off, or that he had miscalculated the brightness and distance of the galaxies. After all, suggesting that most of the universe was made of invisible material was not an easy claim to accept. But Zwicky was right in spirit, even if his methods were crude. His insight planted the seed for one of the most profound mysteries in modern cosmology, the idea that the visible cosmos is just the faint surface of a much deeper, hidden reality. For decades, Zwicky's dark matter remained little more than a curiosity, mentioned occasionally, but not taken seriously. It wasn't until the 1970s that his strange idea resurfaced, thanks to the careful and relentless work of an astronomer named Vera Rubin. Rubin's fascination lay with how galaxies spin. She spent countless nights at the Kitt Peak National Observatory in Arizona, observing spiral galaxies and measuring the speeds of stars at different distances from their centers. What she found changed astronomy forever. In a galaxy, stars closer to the center should move faster than those farther out, much like planets in our solar system, where Mercury orbits the Sun faster than Earth, and Earth faster than Jupiter. The reason is simple: most of the Sun's mass, and thus most of its gravity, is concentrated at the center, so objects farther away feel a weaker pull. Rubin expected galaxies to follow a similar pattern, but when she plotted her data, she found something astonishing. The stars in the outer edges of galaxies were moving just as fast as those near the core. It was as if an enormous invisible mass surrounded each galaxy, exerting enough gravity to keep those outer stars bound in their high-speed orbits. Rubin's findings were so precise, so consistent, that they could not be ignored. Every galaxy she studied revealed the same strange pattern. The implication was undeniable. Most of a galaxy's mass wasn't in its stars, or its gas, or its dust. It was in something unseen. This invisible halo extended far beyond the luminous edge of the galaxy, forming a cocoon of dark matter that provided the gravitational glue necessary to hold everything together. Rubin's quiet persistence turned a strange idea into an accepted truth. Through her work, dark matter transformed from a speculative concept into an essential ingredient of the universe. By the 1980s, more and more evidence began to pile up from different corners of astrophysics. Astronomers studying galaxy clusters confirmed that their motions could not be explained by visible mass alone. Observations of gravitational lensing, where the light from distant galaxies is bent by massive objects along its path, revealed distortions far greater than the visible matter could account for. Even the delicate ripples in the cosmic microwave background, the faint afterglow of the Big Bang, carried the fingerprints of dark matter. These ripples showed how matter was distributed in the early universe, and only models, including dark matter, could reproduce the patterns we see today. Each new discovery reinforced the same conclusion: something massive but invisible must be shaping the cosmos. Scientists began to estimate how much of this unseen material existed, and the numbers were staggering. Roughly 85% of all matter in the universe is dark. Everything else, the stars, planets, interstellar gas, and dust, makes up less than 15%. The world we see is the smallest fraction of what's real. But how did scientists manage to find evidence for something that can't be seen or touched? The answer lies in the elegance of physics itself. Every object in the universe, no matter how faint, obeys the same gravitational laws. When galaxies spin, when clusters move, when light bends, all these motions are governed by gravity. By carefully measuring these motions, scientists can map where mass must be, even if it's invisible. In a sense, astronomers became cosmic detectives, tracing the unseen by following its gravitational fingerprints. The more precisely they looked, the clearer the picture became. Dark matter wasn't just a mathematical trick, it was the invisible skeleton of the universe. As technology advanced, so did our ability to detect dark matter's influence. High-resolution telescopes, orbiting observatories, and deep space probes began to provide data with extraordinary precision. The Hubble Space Telescope, for instance, revealed breathtaking images of gravitational lensing. Distant galaxies stretched and warped into arcs and spirals by the gravity of massive dark matter structures between them and us. These cosmic distortions became one of the most beautiful proofs of an invisible reality. Through them, we could literally see the shape of dark matter's gravitational field, even though the matter itself remained unseen. Meanwhile, on Earth, physicists began building experiments to catch the elusive dark matter particles directly. They constructed vast underground detectors filled with ultra-pure materials, shielded from cosmic rays and radiation, waiting for a single dark matter particle to collide with an atomic nucleus. The goal was simple: to record the faintest, rarest signal from the invisible. Though no confirmed detection has yet been made, every attempt refines our understanding, narrowing the possibilities and sharpening the mystery. The story of discovery doesn't end with observation alone. Dark matter also helps explain how the universe evolved after the Big Bang. In the early universe, ordinary matter was hot, energetic, and full of radiation. It couldn't clump together easily because photons, the particles of light, kept pushing it apart. But dark matter, unaffected by light, could start clumping much earlier, forming the gravitational wells into which ordinary matter later fell. In this way, dark matter acted like scaffolding for the cosmic structure, shaping where galaxies would form, where clusters would emerge, and where the great cosmic voids would remain. The universe as we know it, its grand architecture, its patterns, its galaxies could not exist without it. There's a certain poetic symmetry in how we came to know this hidden mass. It was never about seeing, but about understanding. The discovery of dark matter reminds us that science is not only about what can be touched or illuminated, it's also about the unseen truths that reveal themselves only when we look deeply, patiently, and humbly at the patterns of nature. The astronomers who first noticed these patterns were not searching for mystery. They were searching for balance in the numbers, for consistency in the laws of motion. What they found instead was a revelation, a universe far richer, darker, and more intricate than they could have imagined. As you imagine them now, standing at their telescopes decades ago, measuring the faint light of distant galaxies under a cold, dark sky, it's easy to feel a kind of quiet wonder. They were staring at what little light the universe offered, yet what they found was hidden in the shadows. Their work transformed our understanding of existence. Because of them, we know that darkness isn't emptiness, it's the deeper truth behind the glow of stars, the invisible stage upon which the universe performs its endless, silent dance. If you could step outside the boundaries of the Milky Way, beyond the shimmering spiral of stars and glowing nebulae, and look at the universe from an impossible distance, you would see something breathtaking, not a random scatter of galaxies, but an intricate pattern stretching across the cosmos like lace. Filaments of light and dark weave together, connecting clusters of galaxies across billions of light years. Between them, enormous voids and vast regions nearly empty of matter. This is the cosmic web, the grand structure of the universe. And at its heart lies dark matter, the invisible skeleton that gives the cosmos its shape. The cosmic web is not a poetic metaphor. It is a physical reality, a network of filaments made mostly of dark matter, threaded with galaxies and gas. Ordinary matter, the stuff that makes stars and planets, follows the gravitational pull of these dark filaments, gathering in their densest regions like dew forming on a spider's web. Where filaments intersect, galaxies cluster together, forming knots and nodes of light that mark the densest points in the structure. In between, vast cosmic voids stretch for hundreds of millions of light years, places where dark matter is scarce and galaxies are few. The web connects everything, from the smallest dwarf galaxies to the largest clusters known, tracing the hidden architecture of creation. This cosmic network didn't appear overnight. Its origins lie in the earliest moments after the Big Bang. In those first fractions of a second, the universe was a hot, dense soup of particles and radiation, smooth, uniform, and almost featureless, but not perfectly so. Tiny fluctuations in density, quantum ripples frozen into the fabric of space itself, created slightly denser regions that would later become the seeds of structure. As the universe expanded and cooled, dark matter began to gather around these tiny overdensities. Because dark matter doesn't interact with light, it didn't experience the same pressure that kept ordinary matter from clumping together. It could collapse freely under its own gravity, forming invisible halos, the earliest skeleton of the cosmic web. As time passed, these halos grew and merged, forming larger filaments and nodes. Ordinary matter, influenced by dark matter's gravity, began to fall into these same structures. The invisible web of dark matter became a framework for visible galaxies. Wherever dark matter was dense, gas collected, cooled, and condensed into stars. The first galaxies lit up like small sparks along the dark filaments, tracing the shape of an invisible map that had existed long before light itself. In this way, dark matter shaped not only the large-scale structure of the universe, but also the very birthplaces of light. The cosmic web is, in many ways, the fingerprint of dark matter. When astronomers use computer simulations to recreate the evolution of the universe, they start with the physics of dark matter and gravity. They let these invisible particles interact only through their gravitational pull, expanding the virtual universe over billions of years. What emerges from those simulations is astonishingly similar to what we see through telescopes, a network of filaments and clusters forming a vast three-dimensional web. The galaxies align themselves along these dark matter threads, revealing that the visible universe is just a faint tracing of an unseen design. To visualize the scale of this structure is almost impossible. Each filament of the cosmic web can stretch across hundreds of millions of light years, and yet it is only a small strand in the larger fabric of space. Imagine a vast foam, where each bubble's thin surface is made of galaxies and dark matter, and the empty interior is a cosmic void. The web stretches across the observable universe, connecting billions upon billions of galaxies in a single, interconnected structure. It is both delicate and immense. The universe's hidden geometry. We can actually see hints of this cosmic web, not directly in dark matter, but in the galaxies that trace its outline. Modern telescopes, like the Sloan Digital Sky Survey, have mapped the positions of millions of galaxies across the sky, revealing the large-scale structure of the universe in 3 dimensions. When you look at those maps, you see patterns that resemble veins in a leaf or filaments of frost, long chains of galaxies winding through space. These maps show where dark matter's gravity has gathered ordinary matter, sculpting the cosmos into an intricate lattice of light. The resemblance between these real observations and theoretical simulations is one of the greatest triumphs of modern cosmology. It confirms that dark matter is the scaffolding upon which all cosmic structure hangs. In a quiet way, dark matter behaves like the bones of the universe. It doesn't shine, it doesn't burn, it doesn't decay into something visible, but it gives the universe its strength and form. Without it, galaxies would not know where to form. Clusters would not coalesce. The universe would remain a diffuse mist of gas, unshaped, without texture. Every beautiful galaxy we see is suspended in place by the unseen web that surrounds it, held together by threads of dark gravity that stretch from one corner of the cosmos to another. Gravitational lensing has allowed astronomers to map dark matter more directly than ever before. When light from a distant galaxy passes near a large cluster filled with dark matter, the light bends around it, distorting and magnifying the image we see. By measuring these distortions carefully, scientists can reconstruct the distribution of dark matter in the cluster like a shadow map of the invisible. The results reveal vast halos surrounding galaxies, connected by filaments that extend far beyond the luminous regions. These gravitational maps are our best glimpse of the dark skeleton, ghostly outlines, showing that even where light fades, structure continues. There's something profoundly humbling about realizing that we live inside this invisible web. The Milky Way, with all its stars and planets and nebulae, is not alone, but bound by unseen threads to countless other galaxies. Our local group, the Milky Way, Andromeda, and dozens of smaller galaxies drifts within a filament of the web, moving slowly toward a massive cluster called the Virgo cluster. Every motion of our galaxy, every gravitational tug we feel, part of this cosmic network's silent choreography. Dark matter's role in creating the cosmic web also explains how galaxies evolve. Within the densest knots of the web, gravity pulls matter together so strongly that clusters of galaxies form enormous cities of hundreds or thousands of galaxies bound by gravity. In the thinner filaments, smaller galaxies form and flow along these bridges, sometimes colliding and merging as they travel toward the larger clusters. This constant movement, this cosmic migration, shapes the history of galaxies over billions of years. It is a slow, elegant dance choreographed by dark matter, invisible yet precise, where gravity dictates every step. Even the cosmic voids, the vast, nearly empty regions between the filaments, owe their existence to dark matter. These are the spaces where the density of dark matter is low, where gravity's pull is weaker, allowing the matter to drift away and gather elsewhere. The voids are the silent spaces in the universe's grand composition, balancing the bright filaments of galaxies with oceans of near emptiness. They are the pauses between the notes, the dark spaces that make the cosmic symphony complete. It is tempting to imagine the cosmic web as static, frozen in place across eternity. But in truth, it is alive with motion. Galaxies move slowly along its filaments, like rivers of stars flowing through the universe. Clusters grow heavier as more galaxies fall into them. The web stretches and evolves, changing subtly over billions of years. Dark matter does not sit still. It responds to gravity, pulling and being pulled, shaping the universe's architecture in an endless cycle of creation and collapse. The cosmic web also offers a glimpse into the universe's future. As dark energy accelerates the expansion of space, the filaments will stretch thinner. Galaxies that are now neighbors may drift apart, separated by vast distances they can no longer cross. The web will remain, but its connections will fade slowly, leaving only isolated clusters surrounded by darkness. The grand cosmic structure will become more distant, more quiet, its filaments pulled taut across the expanding fabric of space. To understand the cosmic web is to understand that dark matter is not merely a curiosity hidden in the background, it is the architect of all structure. Every pattern we observe, every galaxy we see through a telescope, every beam of light that travels across the cosmos follows the contours of dark matter's invisible design. We exist not in random isolation, but within a vast, interconnected web, one that began forming billions of years ago and continues to evolve today, shaping the path of galaxies and the destiny of stars. For decades, the greatest minds in science have stared into the darkness, searching for something that refuses to reveal itself. Dark matter, silent, invisible, and seemingly untouchable, is everywhere, threading through the cosmos like an unseen wind. Its gravitational presence is undeniable, shaping galaxies and bending light, yet its true nature remains one of the most enduring mysteries in physics. We know it's there, we can feel its pull, but to touch it directly, to detect even the faintest trace of its substance, is a task that has tested our imagination, patience, and technology to the limits of what is humanly possible. The search for dark matter is a story of persistence in the face of invisibility, of scientists reaching into the dark, listening for whispers in the silence. The first challenge in detecting dark matter is that it doesn't interact with light or with ordinary matter in the ways we understand. Every known particle, from the smallest electron to the heaviest atom, can collide, scatter, or absorb light. These interactions are what make the universe visible to us. But dark matter ignores light completely. It doesn't glow, it doesn't reflect, it doesn't absorb, and it doesn't radiate. It passes through everything, silent and indifferent. This makes it invisible to telescopes, no matter how powerful. So scientists must turn to other methods, searching for indirect signs, tiny effects, or the rarest interactions that might betray its presence. One approach begins deep underground, in the quietest places on Earth, in old mines and mountain caverns, far below the surface where cosmic radiation cannot reach, lie some of the most sensitive detectors ever built. These underground laboratories are designed to catch the briefest flash of light or the smallest vibration that might occur when a dark matter particle passes through and collides with an atomic nucleus. The experiments are shielded by rock and layers of lead to block background noise. The air inside is pure, the instruments cooled to near absolute zero, and the scientists wait in darkness for signals that might come once a year or never at all. It is an act of patience that borders on devotion. One of the most famous experiments of this kind is the Lux Zeppelin detector, buried deep beneath the Black Hills of South Dakota. It consists of a tank filled with liquid xenon, surrounded by sensors so sensitive they can detect the faintest burst of light produced by a potential collision. When a particle of dark matter, perhaps a weakly interacting massive particle, or WIMP passes through, it might bump into a xenon atom, causing a tiny flash of energy. That flash, though unimaginably small, could be the first direct evidence of dark matter. Yet despite years of data and countless improvements, no conclusive signal has yet been found. The detectors remain silent, whispering only the language of hope. Other experiments, like Xenont in Italy's Gran Sasso Laboratory and Pandax in China's Jinping Underground Laboratory, continue the search with increasing precision. Each generation of detectors grows larger, more sensitive, and more carefully shielded from cosmic noise. Some use cryogenic crystals, others use noble gases, but all share a single purpose: to listen for something that may rarely, if ever, speak. These detectors, resting miles below our feet, are like ears pressed to the heart of the universe, waiting for a sound that might take centuries to arrive. But the search for dark matter doesn't stop beneath the Earth. It extends into the skies. Where space-based observatories look for indirect clues, the subtle fingerprints dark matter might leave behind as it moves or decays. Some theories suggest that when dark matter particles interact with each other, they might produce high-energy particles like gamma rays or positrons. Telescopes like the Fermi Gamma Ray Space Telescope scan the sky for these emissions, especially from regions dense in dark matter, such as the centers of galaxies or clusters. A faint excess of gamma rays near the heart of the Milky Way has intrigued scientists for years, sparking debates about whether it might be the first glimmer of dark matter or simply an effect of unknown astrophysical sources like pulsar S. In another approach, physicists turn to the most powerful machines on Earth, particle accelerators. The Large Hadron Collider at CERN, near Geneva, smashes protons together at nearly the speed of light, recreating the extreme conditions of the early universe. The hope is that these collisions might produce dark matter particles that slip away undetected, leaving behind an imbalance of energy that scientists can measure. These experiments don't see the dark matter directly. They see its absence: missing energy, missing momentum, a ghostly hole in the data that might point to the invisible. So far, the collider has yet to reveal dark matter's signature. But each collision adds another piece to the puzzle, narrowing the range of possibilities. While some scientists search in underground labs and high-energy colliders, others look to the cosmos itself, where dark matter's influence shapes galaxies and cosmic structures. Gravitational lensing, where light bends around massive invisible objects, remains one of the most powerful tools for mapping dark matter's distribution across the universe. Observatories like the James Webb Space Telescope and the Euclid Space Telescope are helping astronomers chart these invisible regions in exquisite detail. By studying how light from distant galaxies is distorted, scientists can infer where dark matter lies, how it clumps, and how it moves. It's not a direct detection, but it reveals the outlines of a shadow, the cosmic silhouette of something vast and unseen. There are also experiments that turn to more speculative forms of dark matter, ideas that stretch the imagination beyond the boundaries of known physics. Some physicists propose that dark matter could be made of axions, lightweight particles that might occasionally convert into photons under the right conditions. To search for these particles, scientists use highly sensitive radio detectors placed inside strong magnetic fields, hoping to catch the faint hum of a photon being born from darkness. Experiments like ADMEX, the Axion Dark Matter Experiment in Washington State, are designed precisely for this purpose. They listen to the universe in frequencies of silence, where even a single faint tone could rewrite our understanding of reality. Others explore the idea that dark matter might consist of primordial black holes, tiny remnants formed in the earliest moments after the Big Bang. If these microscopic black holes exist, they would have enormous mass packed into a minuscule volume, behaving gravitationally like dark matter. Astronomers search for their presence by studying how they might bend starlight or distort signals from pulsars. Even though these searches have yet to confirm such objects, they remind us that dark matter might not just be a new particle, but something far stranger, a relic of creation itself. The search for dark matter is as much philosophical as it is scientific. It forces us to question what it means to know something exists. We cannot see dark matter directly, yet its presence shapes the universe so clearly that denying it would mean rejecting gravity itself. It is both real and intangible, both proven and unknown. Every experiment, every failed detection, deepens the mystery instead of diminishing it. But that mystery is what drives science forward. The quiet determination to illuminate what hides just beyond reach. In a way, these searches are acts of faith in the language of physics. They represent humanity's refusal to accept that invisibility equals absence. Each scientist who descends into an underground lab, each engineer who calibrates a detector to impossible precision, each astronomer who studies the faint arcs of light in a galaxy cluster, all share the same conviction that the universe, no matter how silent, is speaking, and it is our job to listen closely enough to hear. Perhaps one day, a signal will arrive, a faint spark in a detector, a missing fraction of energy in a collision, or a subtle anomaly in the light of a distant galaxy. That signal will not only confirm dark matter's existence, but also open a new chapter in our understanding of what the universe is made of. Until then, we remain searchers of shadows, explorers of absence, building instruments delicate enough to measure the invisible, waiting patiently for the cosmos to whisper back. If you could step outside the universe and gaze upon it from an unimaginable distance, what would you see? You might expect to find galaxies scattered randomly across the dark, like glitter tossed across an infinite void. But the cosmos is far more organized than that. Galaxies are not drifting aimlessly. They are arranged in vast, interconnected filaments, immense bridges of matter that stretch across hundreds of millions of light years. Between these filaments lie enormous empty spaces, cosmic voids so vast they could swallow entire galaxy clusters. This grand structure, this intricate network of filaments and nodes, is called the cosmic web, and it is woven almost entirely from dark matter. It is the hidden framework upon which the universe has been built, an invisible architecture that gives shape to everything we can see. In the earliest moments after the Big Bang, the universe was hot, dense, and nearly uniform. There were no stars, no galaxies, just a sea of energy and fundamental particles expanding and cooling. But even then, tiny fluctuations existed, minute ripples in the density of matter that were just slightly heavier in some regions than others. These differences were incredibly small, perhaps 1 part in 100,000. Yet they were enough to change everything. Gravity began to amplify these differences, pulling more matter into the slightly denser regions and leaving the emptier areas even more empty. Over time, these small clumps grew, attracting more mass as the universe expanded and cooled. Dark matter, being unaffected by light or heat, began to clump together first, forming invisible scaffolds that would later guide the ordinary matter, gas and dust, to settle within them. From these seeds, galaxies were born. The beauty of the cosmic web lies in its scale. When scientists use computer simulations to model how dark matter evolves, the results are stunning. Sprawling filaments of invisible mass crisscross the universe, converging at bright knots where clusters of galaxies form. These intersections are the densest regions of dark matter, gravitational wells that attract not only ordinary matter, but also light itself. Between them stretch vast voids, nearly empty expanses, where even dark matter is scarce. This web spans the entire observable universe, a lattice so immense that light takes billions of years to cross from one filament to another. Every galaxy, including our Milky Way, is a single luminous bead strung along one of these invisible threads. When astronomers look at the large-scale distribution of galaxies, they can trace the outline of this hidden framework. Surveys like the Sloan Digital Sky Survey (CDS) have mapped millions of galaxies, revealing a pattern that mirrors the structure predicted by dark matter simulations. It's as if the visible universe is a faint echo of an invisible skeleton, a luminous reflection of something far greater. These galaxy maps are like X-rays of the cosmos, showing us where dark matter must lie, even though we cannot see it directly. The galaxies act as tracers, highlighting the invisible filaments that bind them together. One of the most astonishing aspects of the cosmic web is that it appears to connect everything. The gravity of dark matter filaments acts like cosmic highways, guiding the motion of galaxies and clusters over billions of years. Even the gas that forms new stars flows along these filaments, channeling into galaxies that lie at their intersections. Without these dark matter bridges, the universe might look completely different, more scattered, less structured, and perhaps even incapable of forming the rich variety of galaxies we observe today. Dark matter doesn't just hold galaxies together. It connects them in a vast, interwoven pattern that defines the very shape of the cosmos. In a sense, dark matter acts as the cosmic architect, laying the foundation upon which everything else is built. Its gravity molds the universe, dictating where light can gather and where darkness must prevail. When we look at galaxy clusters, the largest gravitationally bound structures in the universe, we see dark matter's influence most clearly. These clusters contain hundreds or even thousands of galaxies, all moving in a complex dance governed by the invisible mass that surrounds them. Astronomers studying the Bullet cluster, for instance, discovered that the visible matter, the hot gas emitting X-rays, made up only a fraction of the total mass. The rest, the vast majority, was dark matter, revealed only through its gravitational lensing effects. This observation was one of the most powerful confirmations that dark matter truly exists, because it showed that mass and light can be separated, the unseen outweighing the seen. Through gravitational lensing, dark matter's invisible structure becomes visible in another way. When light from a distant galaxy passes near a massive cluster or filament of dark matter, the gravity of that dark matter bends and distorts the light, like glass, warping an image behind it. By studying these distortions across large patches of the sky, astronomers can reconstruct maps of dark matter's distribution. These maps reveal intricate filaments, arcs, and halos, the very skeleton of the cosmic web. The result is like watching the universe's hidden bones glow faintly in silhouette, a delicate reminder that light travels along paths sculpted by the unseen. The cosmic web is not static. It evolves over time. In the early universe, the filaments were thinner and more diffuse, but as billions of years passed, dark matter's gravity pulled them tighter, drawing more gas and galaxies into their embrace. The knots at the intersections grew into galaxy clusters, while the voids between them expanded, becoming great empty abysses that stretch for hundreds of millions of light years. In this dynamic process, dark matter acts like the frame of a growing organism, invisible but essential, guiding the formation of everything else. Our Milky Way is part of this immense network. It resides within a filament that stretches between other clusters and galaxies, all linked through the gravity of dark matter. If you could somehow see dark matter, our galaxy would appear not as an isolated spiral drifting in darkness, but as one glowing node in a vast network of threads, like a single neuron in a cosmic brain. The idea that everything, every star, planet, and life form is connected through this hidden web is both scientific and deeply poetic. It reminds us that even in the cold emptiness of space, there is structure, coherence, and an underlying order that transcends the limits of sight. Recent missions like the Euclid Space Telescope, launched by the European Space Agency, are now mapping this invisible architecture in greater detail than ever before. By studying how billions of galaxies are distributed and how their light is bent by gravity, Euclid aims to build the most detailed three-dimensional map of the cosmic web yet. Its observations will not only reveal how dark matter is arranged, but also how it interacts with another mysterious component of the universe, dark energy, which drives cosmic expansion. Together, these two forces, unseen, yet dominant, shape the destiny of everything. What makes the cosmic web so mesmerizing is its resemblance to natural patterns we see elsewhere. The branching of rivers, the filigree of frost, the structure of neurons in a brain. Nature seems to repeat itself on every scale, from the microscopic to the cosmic. The universe, in this view, is a living system, its filaments pulsing with galaxies like veins carrying the lifeblood of creation. And at the heart of it all is dark matter, silent and invisible, but undeniably real. It does not shine, it does not speak, yet its gravity hums through everything, binding the cosmos into a single, interconnected whole. As scientists study this grand design, they realize that dark matter's presence is not merely a background phenomenon, it is the very reason structure exists at all. Without its gravitational pull, the early universe's gas would have expanded too quickly for stars or galaxies to form. The night sky, as we know it, would be empty. Every twinkling star, every glowing nebula, every spiral galaxy owes its existence to the invisible framework of dark matter. The cosmic web, though unseen, is the stage upon which all the light of the universe performs. In every direction we look, the traces of this hidden architecture can be found in the motion of galaxies, in the bending of starlight, in the echoes of the Big Bang itself. Dark matter is the silent artist behind the masterpiece of the universe, drawing its lines not with light, but with gravity. The filaments stretch endlessly, weaving galaxies together across time and space, holding everything in delicate, invisible balance. And somewhere, beyond the reach of our instruments, that web continues to grow, its threads tightening, its knots deepening, its structure whispering the quiet harmony of a universe held together by darkness. Gravity is the quietest of forces, yet it is also the most patient, the most relentless, and the most powerful sculptor of the cosmos. It doesn't shout like the crackle of electromagnetic energy or the explosive bursts of radiation from stars. Instead, it whispers a soft, invisible pull that tugs at everything with mass. And in that whisper lies the story of how dark matter shaped the universe. Though unseen and untouchable, dark matter's gravity weaves the cosmic fabric, determining where galaxies form, how stars gather, and how the universe itself unfolds through time. Every cluster, every spiral arm, every faint shimmer in the night sky, is a silent echo of its pull. When we think of gravity, we think of the familiar: an apple falling to Earth, the moon circling our planet, or the Earth orbiting the sun. But the same law that governs these small motions also commands the vastest scales of existence. It is gravity that gathers dust into stars, stars into galaxies, and galaxies into clusters that stretch across billions of light years. And at the heart of this grand cosmic dance lies dark matter, the hidden mass that amplifies gravity's influence far beyond what ordinary matter alone could accomplish. If the universe were a vast symphony, gravity would be the rhythm, and dark matter would be the deep, resonant bass that gives it weight and structure. In the early universe, just a few 100,000 years after the Big Bang, everything was still a hot fog of hydrogen and helium. Light was just beginning to move freely through space, and the cosmic microwave background, that faint afterglow of creation, carried the imprint of the universe's first structures. Within that glow were subtle fluctuations, tiny variations in density that would one day grow into galaxies and clusters. Dark matter, being unaffected by radiation, began to gather first. Its gravity pulled together regions of slightly higher density, forming halos, invisible spheres of mass where gas and dust would later collect. These halos became the gravitational seeds from which galaxies grew, each one a well of darkness cradling the light that would follow. As billions of years passed, the gravitational pull of dark matter guided the evolution of the cosmos. Ordinary matter, cooling and condensing, fell into the gravitational wells created by dark matter, igniting the first stars and forming the earliest galaxies. These galaxies then merged and collided, their orbits and trajectories choreographed by the deeper, unseen forces surrounding them. It was dark matter that ensured galaxies could stay bound together even as they spun at dizzying speeds. Without its extra gravity, stars at the edges of galaxies would fly off into space, their delicate spirals unraveling. The whisper of dark matter's gravity holds them fast, binding light and matter into luminous structures that persist across cosmic time. Astronomers have observed this invisible pull not only within galaxies, but across vast distances between them. The way galaxies cluster together in large-scale patterns, forming filaments, walls, and voids, follows the gravitational landscape carved by dark matter. Where the invisible mass is densest, galaxies gather. Where it is thin, space yawns open into emptiness. The entire visible universe, every shining star and glowing nebula, traces the outlines of a structure that gravity built, a skeleton of darkness stretching across the heavens. The most direct evidence of this gravitational influence comes from the phenomenon known as gravitational lensing. When light from a distant galaxy travels through space and passes near a massive object, the object's gravity bends the light, distorting its path. This bending can magnify, twist, or duplicate the background galaxy's image, creating beautiful arcs and halos of light. But often, the amount of bending observed is far greater than what visible matter alone could produce. The missing mass, the extra gravity needed to account for the bending, must come from dark matter. In this way, light itself becomes a messenger of darkness, revealing the invisible through its curved journey. Some of the most striking examples of this effect are found in galaxy clusters. Enormous gatherings of hundreds or thousands of galaxies bound together by gravity. When scientists map the gravitational lensing around these clusters, they find that the bulk of the mass is not in the galaxies or even the hot gas that fills the space between them, but in something unseen. The Bullet Cluster, one of the most famous examples, provides a cosmic X-ray of this phenomenon. Two clusters collided billions of years ago, their hot gas colliding and slowing down, while the dark matter halos pass through one another almost unaffected. Observations of this event showed that the centers of gravity traced by lensing were separated from the luminous gas, offering direct proof that most of the mass in the cluster was invisible. It was one of the clearest demonstrations that dark matter's gravity truly shapes the universe in ways that light cannot. The whisper of gravity extends even farther, beyond galaxies and clusters, into the large-scale flow of the cosmos. Over billions of years, dark matter's gravity has slowed the universe's expansion, tugging at the galaxies as they drift apart. Without this invisible weight, the cosmic expansion might have raced ahead too quickly for stars and galaxies to form. But gravity, patient and persistent, counterbalanced that expansion just enough to let matter gather, cool, and ignite. The universe's very ability to host light to create suns and planets and life owes itself to the quiet persistence of dark matter's gravitational pull. Even now, dark matter continues to shape the evolution of galaxies. Simulations of cosmic formation, powered by supercomputers, show how dark matter halos act as anchors in the vast ocean of space. As galaxies form within them, smaller halos merge into larger ones, creating the hierarchical structure we observe today. These simulations, visualizing billions of particles of dark matter over cosmic time, reveal a universe alive with motion and connection. Filaments stretch and twist, knots tighten, and clusters form where threads intersect, all under the guidance of dark matter's gravity. The patterns are not random, but harmonious, echoing the same physics that governs the fall of an apple or the orbit of a planet. It is gravity on the grandest scale, sculpting the universe with invisible hands. Yet, even as gravity's effects are unmistakable, the nature of the force itself remains deeply mysterious. Einstein's general theory of relativity describes how gravity works, how mass curves spacetime, and how objects move along those curves. But it doesn't explain what dark matter is or why it behaves as it does. It is as though we understand the music, but not the instrument playing it. Some scientists wonder whether dark matter might not be matter at all, but a sign that our understanding of gravity is incomplete. Could gravity itself behave differently at cosmic scales? Could there be hidden dimensions or subtle forces that mimic the effects of dark matter? These questions remain open, and their answers could reshape our entire understanding of the universe. For now, gravity remains our most faithful guide to the invisible. Every time a galaxy rotates, every time light bends around a massive cluster, every time the cosmic web stretches across space, it speaks in the language of gravity, a language dark matter understands intimately. Its whispers are everywhere, though we need sensitive instruments and careful observation to hear them. The subtle motion of stars, the expansion of space, the ripples in the cosmic background radiation all carry traces of that quiet force, that unyielding pull of unseen mass. When we look at the night sky, we are not merely seeing stars, we are seeing the result of billions of years of dark matter's quiet work. Each glimmer of starlight, each cluster shining faintly through space, is a note in the cosmic melody composed by gravity and conducted by the unseen. The whisper of dark matter's gravity continues even now, shaping the universe's fate, guiding its expansion, and binding the light that fills it into the grand pattern we call the cosmos. As we reach the end of our quiet journey through the cosmos, The story of dark matter lingers like a whisper in the vast night sky. We began with the visible, with stars that shine, galaxies that spin, and light that travels across billions of years, and yet, beneath it all, there is something far greater that we cannot see. Something that shapes the motion of everything we know. Something that silently binds the universe together. Dark matter is not just a scientific mystery. It is a profound reminder of how little we truly see of the world around us. For every glowing star, there are countless invisible threads of matter weaving the cosmic web, holding galaxies in their embrace, guiding the dance of gravity that sculpts the universe into its grand design. It reminds us that what is unseen is not unimportant. That often, the most powerful forces in existence are the ones we cannot touch, cannot hear, and cannot measure directly, but can only sense through their influence on what is visible. In the dark matter of space, we see both the limits and the beauty of human understanding. We have built instruments that can see to the edge of time, that can measure the flicker of a single photon, that can listen to the echoes of the Big Bang itself. And still, the mystery endures. Yet that mystery is not a void. It is a frontier. It is the quiet promise that the universe still holds secrets worth dreaming about. Perhaps one day, the darkness will give up its secrets. Perhaps a faint signal will flicker in a detector, or a new particle will appear in the data from a collider, or a distant galaxy's movement will tell us what we've been searching for all along. Or perhaps the answer will be something even more extraordinary, something that changes how we think about matter, energy, and reality itself. But tonight, under the hush of the stars, it is enough to simply wonder, to know that beyond every point of light, there lies an ocean of the unseen. Vast, patient, eternal. Dark matter humbles us, and in its silence, it invites us to listen. So as you drift towards sleep, let your thoughts float through that invisible universe, through the quiet gravity that holds the galaxies, through the calm fabric of space itself. The cosmos, in all its mystery, keeps turning softly, carried by forces beyond our sight. And somewhere in that darkness, the story of everything continues, written in the language of the unseen, spoken only in the stillness of the stars.